this is our starting point. So if you know what it means, right? First, you have to understand that this is a vector equation. So it has three components: x1, x2, and then x3. These are referred to as the medial coordinates, and this is the spatial coordinates. So what this means is that the medial coordinates correspond to the coordinates of a fluid point at some reference time, which we are not bringing into the picture. So that is this. So what this says is that the coordinates of that same point, which occupied coordinates psi1, psi2 and psi3 at a reference time, its coordinates at a time t is given by x1, x2 and x3. Not only that, there exist functions x1 cap, x2 cap and x3 cap, which are functions of psi1, psi2, psi3 and time, which give these values. That is all it means. It is justified, or what is the basis of this? That is now immaterial. We will assume that this is given to us as a rule, because this is the basis. We don't really come back to this very often. This is the starting point. You may even forget about this starting point, because all the quantities that we are now going to define and which we will use, for which we will develop equations, many will be based on this. For instance, the velocity. Velocity is defined as the time derivative of this function. So, when I put the cap on it. Again, it has three components. So, I won't be writing this component form all the time. So, this is the, probably the last time I will write this in this detailed manner. You have to understand the notation properly. These are the three components of the given in terms of this basic transformation. The time derivative of x1, x2 and x3 expressed as a function of psi and t. So we are following the medial point. That's what it means with time. Right? So its velocity is medial point is identified by psi. It is at a location x1. Its instantaneous velocity is given by the derivative of that function. Similarly, the acceleration is either can be defined as t squared or is given by the time derivative of the velocity, the second derivative with respect to time of the position. So now you can see here the x1, x2 and x3 expressed as functions of psi and time. So when you differentiate it with respect to time, you get another function of psi1, psi2, psi3 and time. So there is no confusion there. Similarly with the acceleration. However, we will now bring in the spatial description, because what I said was that on top of this assumption, also we assume that the medial coordinates in turn are given by inverse functions that we call as psi r. Right? So there is a one-to-one correspondence where I associate a fluid point at a location, then I can associate with it one and only one material point with coordinates psi1, psi2 and psi3. Those are given now by this inverse function which expresses psi as a function of x and t. This is important to understand. In practical problems, we will be dealing only with the spatial description. So what this means is that now, for instance, I have E1, which is expressed as a function of, let me call it sine and tan. That is what you can directly see from this definition. However, on account of this, which expresses the sine in terms of x and t, I can write this as, and this now becomes a function of x and t. Because the sine can be expressed as a function of x and t, I can express a function which by definition is a function of sine and tan in terms of x and tan. So this is very important to understand. This is what is called as the material description. And this is what is called as the spatial description. It's the same quantity. Same quantity. When it is expressed in terms of material coordinates, it is called as a material description. When it is expressed in terms of the spatial coordinates, it is called as spatial description. This I can do for any quantity associated with the fluid motion, not just with the velocity. It can be done, for instance, for rho. For instance, if I am talking about, let's look at the inverse. Let's talk about rho, which is expressed as a function of the spatial location at time t. So what this means is that at time t, I will locate a point which has coordinate x, and I can easily talk about the density at that point and at that instant of time. Right? So I choose a time instant. I choose an arbitrary location in space. Certainly that location will have the fluid is flowing through this region, right? So I have fluid here. The fluid's properties, density, velocity, etc., can be specified as a function of x and time. Okay? So now, because x in turn can be expressed as a function of sine and time, the rho can also be expressed as a function of sine and time. So I can either say the density of a fluid point which occupies a location x at time t, which is what I say when I write it like this, or I can say the density of a fluid point at time t whose material coordinates are given by sine. Both correspond to the same quantity. Because I know that I can back transform and find the corresponding sine, I can either say that the density of a fluid point whose spatial location at time t is specified, or whose material coordinate is specified. Both are equivalent descriptions. Same quantity expressed in terms of different variables. Just like those of you who have seen in thermodynamics, I can, for instance, first start with the entropy or the internal energy expressed as a function of entropy and volume, specific entropy and specific volume. I sort of know that the specific entropy can be expressed in terms of volume and temperature. So that means this now can also be expressed as a function of volume and temperature, or any other pressure and temperature if you want. I can express a variable in terms of any sets of variables in thermodynamics. Here I am choosing two sets. One is the time and the spatial coordinates. Another is the time and the material coordinates. So, material coordinate is fundamental. That the laws of mechanics are, as we said, stated in terms of the body, looking at the body in motion. So the material coordinate is important from that point of view, as we will see. But for practical purposes, they we are not interested in following what happens to medieval point, but we are interested in having what happens to the fluid properties and its changes in a particular location. Right? So we are practical purposes, we need to go to the spatial description, but a very important aspect of the initial part of the course is your familiarity with these two descriptions and your ability to go from one to another without any problem. So first, as an example, we will now see how the derivatives of a particular quantity are in the two descriptions are related. And for instance, in thermodynamics, I can ask what is, if I write this dE by dV, it has no meaning because I haven't said what the other variable is. I put a partial sign, and I know that for pure quantum specific eternity depends on two variables, at least in general. So for ideal gas, it depends on your temperature. So unless I put what is kept constant, this derivative is not complete. So if I put else, then I am really referring to this description. Right? That the internal energy is expressed as a function of entropy and volume. If I, however, I do this, then clearly I am referring to the internal energy expressed as a function of volume and temperature. And what is the relation between the two derivatives? It's an important question. How are the two derivatives related? And that's given by the chain rule we have used extensively to get these derivatives. In the same way, I will have to take a scalar function f, which can be expressed as a function of x and t, or can be expressed as a function of psi and t. The quantity is the same, so I can either write f is equal to or now the question is, what is the difference between df by dt? So you may think I have violated the rule, right? Because I haven't specified what is kept constant, but it's obvious from the context because I have distinguished the two functions. So clearly when I write this, the meaning of this is df by sine kept phase, and the meaning of this is df by dt. Both are equivalent ways of writing the same quantity. How are these two derivatives related? That is the question. This is now to do that, we will look at f. So I can start with any one, but I am starting with this. This is the easier one to do. And then it becomes expressed as a function of. So I am regarding the functional representation in terms of the material coordinates and time as arising out of the functional representation in terms of the spatial coordinates. And this representation is facilitated by this transformation. So clearly, now there are three variables here. That is something which you should keep in mind. So when I write df and by dt, which is df by dt, I'll get four terms actually, because this is derivative with respect to time. So I'll get a term arising out of the derivative with respect to time here. So this would be f by dt at x. So I'll write that term first. Plus I'll get three terms because each one of the spatial, this is the chain rule. So if you're not following what I am doing, you have to go back and check what the chain rule means. You cannot be going over it again and again, right? Or again, because this is something you're supposed to know. Right? So there are three variables here, x1, x2, and x3, each one of which is dependent in general on sign and time, because our derivative is with respect to time. So that will now be sum over I equal to 1 to 3 df by dxi, right? df by dxi, and I can put a bar, times dxi by dt. This is a chain rule. df by dx, the original variables are x1, x2, and x3. My derivative is with respect to time, so I have to differentiate x with respect to time. First take the derivative with respect to x, the original variable. Now the new variables are psi and time. The derivative is with respect to time. So this is the form that the chain rule would take. And on top of it I have, this is basically df by dt times dt by dt. This also has the same form, but t is transformed into itself. That is not transformed. That's not a new variable. It's already there. So there are four transformations. x1 going to psi t, x2 these are all the same, and then t going to itself. So we are getting four terms in the chain rule, right? The term involving time would be actually effectively df bar by dt times dt by dt. Derivative of time with respect to itself, which is 1, and then you have the other four terms. Now clearly, I have just written it there, dxi by dt is nothing but the ith component of the velocity. So I can now write this as df bar, or let me write it clearly here. I can now write it in this way, df cap by dt slightly differently, di df bar by dxi, I equal to 1, 2, 3. So I now introduce certain notation. This is what it is actually. This is the formula. We write it in a more familiar form. But this is still different. So the material derivative, which is often referred to as a substantial, or the material derivative of any function with respect to time, means we are looking at the representation of that function as a function of the material coordinates and time. That derivative is equal to the spatial derivative. That means that is the derivative with respect to time when the function is expressed in terms of the spatial coordinates and time. That is not, the two are not equal, but they are actually given by the sum, which is sum of bi times df bar by dxi. So from we now simplify the way of writing this by using certain vector operations. The first is scalar product of two vectors. So they have two vectors A, and A is given by A1, A2, A3, those are the components. And the vector B. Right, so this is all assumed that I am talking about a rectilinear or rectangular Cartesian coordinate system. no curvilinear coordinates. We are going to restrict ourselves first to the simple coordinate system geography or very familiar. So now A dotted with B is defined as sum over I equal to 1 to 3 AI BI. This is the scalar product of two vectors, or what is often referred to as a dot product of two vectors. I prefer scalar product because it is two vectors. The operation finally yields a scalar. Because I have two vectors, but when I form the scalar product, net result is a scalar, which is simply given by the sum of the product of the components of the two vectors. This is something you are all very familiar with, scalar or dot product. That is what is scalar. I introduce another quantity or operator now. It's the vector operator called the gradient of a scalar. Scalar I can choose as phi just to distinguish it from F. Any scalar can be. So the gradient of a Cartesian, rectilinear Cartesian coordinate is given by this with the vector sign below. It's a vector operator. It acts on a scalar and it's given by, it's now a vector, right? So the vector is df by d phi by dx1. Scalar is a function of x. It could be a function of time also. This is now with respect to the spatial distance. The gradient operator is always with respect to the spatial description. You can put a transpose here if you want, but I mean basically these are the components of the vector. Because normally we write a vector in column form, but here I hope there is no confusion. These are the three components, whichever way you want to write. Only when you bring it into operation, like multiplying a matrix, we have to write it in a proper way depending on the nature of the operator. As of now, there is no confusion. Clearly, now, this combining these two operations that I have just introduced, this formula can be written as sum over I equal to, or rather compactly as V, the velocity vector, dotted with the gradient of F. So this is the main formula that's coming out of the chain rule. Now I introduced two operations which probably most of you are familiar with, the scalar product of two vectors and the gradient operator vector operator of a scalar. And by combining these two operations which I have introduced, it can be written in a very compact form. Now we will introduce more convention and notation, which you should all be familiar with. So I don't want to write this cap and bar anymore. So what is conventionally done is the quantity is F, right? So this derivative is represented as df by dt, the capital D. Now this derivative is simply written in the usual partial derivative manner. This is just a convention. It concedes the fact that you have to now know that whenever I write some quantity like this, the f is automatically expressed in terms of the spatial description. You won't write a bar and cap and all. It's automatically understood. The reason, what you have to understand is that both are partial derivatives. This is not some new mathematical operation that we have introduced in fluid mechanics. It's as much a partial derivative as this partial derivative. But by convention, the spatial is denoted with the usual partial derivative and a new symbol is introduced for the substantial or material, or I don't know what other terms are used, derivative with respect to time. So whenever I write this, it means that I am referring to this representation that is to be understood. Now, there is some more conventions. One is called as the repeated index summation convention. Short and form can be. This is again a convention that is used quite often in fluid mechanics, because we keep doing the summation again and again and again. Many products, vector products, scalar products, the summation will occur. And I just want to simplify the way of writing by avoiding writing the sum I equal to 1 to C or J equal to 1 to 3 or K equal to 1 to 3 again and again and again. So the repeated index summation convention says that if in a product, if in a particular term, to be a product of anything, obviously involve at least two factors. If the index, particular index is repeated more than once, right, then I will automatically assume that there is a summation over that index, and I don't have to write the sum I equal to 1 to C. For instance, as an example, A dot B, so I simply write it as AI BI. Normally, if I write AI BI and leave it, I could be 1, I could be 2, or I could be 3. It just refers to a term. But however, if I look at this product now, the I is repeated twice. So if I assume the repeated index summation convention, that means this is equal to sum over I equal to 1 to C AI. But I'm just suppressing this by assuming the convention. For instance, even a vector would normally write, for instance, if I represent the unit vectors along the 1, 2, and 3 directions as E1, E2, and E3. They are the unit vectors. That means they are along the 3 axes, but they have a unit length, each one of them. So any vector, I would normally write it as A is equal to A1, E1. This is the full vector form in terms of its components. Plus A2, E2 plus A3, E3. Normally to avoid writing these terms, so the summation sign itself is a simplification so that I don't have to write the whole term, set of terms every time. Right? So normally I would write this as this all of you the explanation of the summation sign. When I write it, you know that I has to be sum 1, 2, and 3. You have to form the sum for 3 terms. Now with the repeated index summation convention, I could simply write it as AI EI. You can see the simplification that results. Again, there is a sum over I because I is repeated, so it means automatically it is sum I is sum from 1 to 3. So it is A1 E1 plus A2 E2 plus A3 E3. So now, so this doesn't change. I can write this as another convention, that notation that I would introduce is d phi by dxi. Again, this is for simplification. I will simply write as phi comma I. It often causes confusion among students, but for my purpose, if you want, you can write it as df by dxi. But again, I will for simplification, because I don't want to write these terms again, I would simply denote it as comma I, which means d phi by dxi. I'm referring to that one particular partial derivative. So the whole formula, for instance, the gradient can be very compactly written as the full vector. So if I want to denote, see, I can either choose to write a vector. For instance, if I want to write a vector, I can simply choose to write an arbitrary component of the vector. So if I want to express this formula, I can write it as I equal to d phi by dxi. So if I express an ith component without specifying whether I is 1, 2 or 3, that means I can write down any of the 3 components. One simple formula is sufficient. So I am writing only the component of the vector. So I want to write the full vector. Obviously, either I can write it like this, give the components, or I can write this as sum over I equal to 1 to 3 df d phi by dxi times ei. This is written there. If I now introduce the comma I notation, then this will simply become phi comma I, and this will become that's all. So typically, to avoid writing down too many terms, whenever I deal with a vector, I will simply write the ith component. So I want to introduce a new operation, just as I have done here. Okay, I am writing all the terms. So I write the ith component is sufficient to explain how to write down all the components of the vector, and the full vector you can easily write. So that is the point. If nothing is there, so if here there is nothing, it is a scalar. There is no ith component for that. So this is what it is. And if now, after explaining all that, if I write it in this way, this is a very famous and important formula which expresses the substantial derivative in terms of the spatial derivative. Often it is written in operator form, and the operation d by dt is given by the operation partial spatial derivative d by dt plus p dotted with the operation. It can act on anything. Sometimes this is surplus, can be density, or also we haven't seen how we have assumed that f is a scalar, so it can be the density. Now we want to write how the substantial derivative of the vector v would be. Right? So then it's easy to do. We introduce that also later, but all I have to do is, since every component of a vector is a scalar, I can take component by component and compute and then put everything together. For instance, if I want to write this, it is perfectly justified to write this, use the same formula to write it in this way, but I am not going to do it now because I have introduced what is the gradient of a scalar. I haven't introduced what the gradient of a vector would be. It would actually be a second order tensor. If we assume that, then I have to explain what I mean by the dot product of a vector with a second order tensor. So I am not going to explain it now, we will explain it later. Right? But however, if I want to simply calculate, so what would I do? I can use the same formula. There is no problem. This is a scalar. This is also a regular scalar derivative. And then I have the gradient of a scalar, which is a vector. The dot product of a vector with a vector we have defined. So what I will do is calculate each one individually and then write it as and so on. Calculate dv1 by dt, that would be the, this is the acceleration actually. component, first component of the acceleration. Then I get the second component, the third component. I can combine. We later write a more simplified and compact expression for that. So right now, even a vector you can quite easily handle by simply doing it component by component. So the substantial derivative of a vector can also be calculated. Are there any questions? Because this notation, this convention, you have to very clearly understand. These are all standard Aris even Birchwood language have. This convention is from article by 7, which I have given in the reference, which I have given in the sheet handed out. So that is somewhat obscure. I haven't seen it very often. It's just more convenient. But either probably you can look at Aris is good for these vector and tensor operations. Birchwood would have them all in the appendices. So I would urge you to look at Aris. It's better and more clearly explained. So this sort of completes the relation between the substantial derivative and the spatial derivative of a scalar. More importantly, also, equally importantly, we introduce so many conventions and operations which will be of great relevance as we go along. Now, look at the meaning of this. In mathematics, you derive the formula. The meaning is you have to be clear, because now we are going to move to calculating the spatial and substantial derivative, the relation. When you have an integral, because we have seen that this can, for instance, be rho or v or whatever. This would come in handy. But we have seen many of the quantities, like the mass of a body of fluid or the mass of a fluid enclosed in a region, or the momentum of the body as a whole. They are written as integrals of some density over the volume. Now, an important question is, what is the relation between the spatial derivative of such an integral and the material derivative of such an integral? That is obviously a more complicated thing to explain. It is what we are going to take up. But because here we are dealing with only a single point, there we are dealing with a collection of points, because that's what a region is integrating over the volume, considering an infinite number of points. You have to be more careful while doing it. But point here is that when I, let us say this is a time t and the fluid point is occupying a position x. So now, if I am calculating df by dt, that is the spatial derivative. So that means what I am doing is I am just focusing on this point. I don't shift my gaze anywhere else. I am just focused on that point. Now the time is going to change. This is at one instant of time. At the next instant of time, this fluid particle is going to move somewhere else, but I am not following that. I am focused here. Some other fluid particle is going to come. Right? So that is what this derivative, what is the change with respect to time? Focusing on one point, that is the spatial location. And focus on that could be the density, for instance. The density at time t is something. The next instant, I am still focused here. What is the density? It could change because the fluid is flowing and many things are happening. So this is this. Now, consider the scene. Now my focus is no longer on the location, spatial location at time t, but now my focus is on the material point. This is obviously more difficult because I now have to, I cannot just sit and watch this point. I have to now follow this as it is moving, the same point, and calculate the time rate of change associated with that. So here I am following a point in motion, same point. Here I am focused on a particular location. That's what this means. The two derivatives physically, that is what it means. This is important because now when we are going to evaluate the integral, it becomes quite confusing. The same idea holds. Now what I will consider is some quantity which is an integral of some function. So I am considering now a region in space. I am not looking at it whether it's a body or what it is, whether I am going to follow the motion of the body or not. So I am taking a time, but I am now considering the full region. T at this time. So some quantity is there. For instance, if you want, you can take it as a density, then we give the mass. Or we can also calculate rho to, because we are restricted to scalar. I mean, this is not a serious restriction because we want to calculate OB dt. Also we take OB I dt. And so the formula still can be assembled as we pointed out in the case of the derivative of a function. Right? So this is now an integral. I can call this capital F. So if small f were low, right, then it would give the mass of the fluid in that region. If I replace it by rho v1, then it will give the component of the first component of the momentum of this body of fluid. Now I can ask, what is the difference between the f by dt problem here is because the variables you have to understand, there it is very clear, f is expressed as a function of xt or they are very explicit. It's very easy to look at the derivatives. Here, you have to understand first what this quantity is. They are now integrated over the whole space. So this is really a function of time only. Because I have a quantity, it depends on the location as well as time, but I am now integrating it over the whole volume. So if I integrated it out, then it becomes a function only of time. Now I want to take the time derivative, but you can still talk about whether it's a spatial time derivative or a substantial time derivative. It's a bit difficult to see because you know once it's integrated out, you don't quite see x or psi there, right? But the meaning is obtained by looking at the physical picture. So, but this is the easier to handle. The spatial derivative is now the same idea. I am focused rather than on a single point. Now this whole region I am focused on. I am not going to move anywhere else. Right? So my attention is focused on this region at all times. So at time t I have this. Now at time let's say t plus delta t. So this is the time t. At t plus delta t also I am focused on the same region. Obviously, there are going to be changes within this region. Some more fluid has come in and its properties will be different. Right? So, what is the change of this integral? Right? Focusing on the integral is over the same region in space. So, that is why this is easier because the domain of integration, we run out of time, is fixed in time. The domain of integration is not going to change. Whereas, what about now the substantial derivative of this integral? Then, at time t, right here, the substantial derivative of this integral, I have now to follow, regardless as a body, and follow and see where it is moving and what position it has occupied at t plus delta t, and has to calculate the changes between this. So this is the important thing. So clearly to calculate this derivative, my domain of integration at time t was this, but my domain of integration at time t plus delta t is shifted. So you all know that formula, for instance, if I have a simple integral a to b f of x dx, it is very easy to calculate. The domain is fixed, but we can also have cases like, for instance, f is a function of two variables. The limits of the integral can depend on one of the variables, right? In which case, there is a formula called the Leibniz rule. It will tell you how to calculate the integral. So to calculate this, the derivative of the integrals, that is where we will see that in theory next class. The derivative of this integral, to calculate that substantial derivative, we have to develop a generalized formula for the so-called Leibniz rule to 3 dimensions. That's basically what we have to do. We'll take that up in next week's class.